Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all. I hope you're all in a good condition. We are from Group 6. So my name is Huzairi Iskandar bin Zaharuddin. These are all my group members. First, Irfan bin Sasaidi. Next is Akram Mujahid bin Abdul Halim. Then Muhammad Faris Firdaus bin Hadi. Next is Muhammad Firdaus bin Muhammad Zawawi. And the last one is me, Huzairi Iskandar bin Zaharuddin. Okay, we move to our topic. Our topic is the downstream process. So from the downstream process, we have ammonia synthesis, methanol synthesis, and the last one is the Fischer-Tropsch synthesis. Okay, let's go. First of all is ammonia synthesis. Ammonia synthesis is a very important process in chemical complex because ammonia is the initial chemical material for a variety industry such as chemical fertilizer, explosive materials, polymers, and coolers. Then the production history of ammonia. In 1774, the first isolated cases of ammonia has been discovered. Then, in 1905, Birkeland and I succeed in producing CaNO3 from the air. After that, in 1913, the Haber-Bosch process was developed. This process has been used even now in many factories for ammonia production. Then, Adolf Frank and Nicodem Carroll found that N2 could be fixed by calcium carbide to form calcium cinamide, which could then be hydrolyzed with water to form ammonia in 1989. Then we back to the Haber-Bosch process. This is the reaction in Haber process. Ammonia process is an equilibrium limited exothermic reaction, which the temperature is around 975 to 770 Kelvin, and the pressure is 100 to 250 bar. So this process is a high pressure and low temperature. This reaction also is low single pass conversion rates around 20%, so large cycle steam is needed that lead to the accumulation of inerts in the loop gas. So this is the simplified flow sheet for the ammonia synthesis. It starts here where the makeup gas, which is N2 and H2, will combine together, then it will flow to the reactor, and then will go to the separator, which it will separate ammonia and the purged gas, which is unreact H2 and N2. This purging gas might be removed or it will be recycled for the next process.
Assalamualaikum, my name is Faris and my matric number is 11823330. So right now I will present to you about ammonia synthesis reactors, continuing from Huzairi's lessons. So right now there are two diagrams in front of you. The schematic diagram shown to you in the left hand side of the slide is the overall process involved to get ammonia. And at the right hand side of the slide, we have the basic shortcut way to understand what processes involved. So in short, the ammonia is converted in the very end of the processes. So each of the processes have their own settings and conditions. As for ammonia synthesis, its pressure is higher than others, with 60 to 180 bar than 25 to 100 bar. So this is as low enough to keep the cost down and high enough to achieve the acceptable yield of product. Next, the single pass conversion is low, that is 20 to 30%. So since the reaction is limited by equilibrium and hence recycling is necessary. So Fritz Haber, the inventor of the Haber-Bosch process, found out that the amount of ammonia produced was far too low, this number 20 to 30%, and too low to be commercial interest. So he invented recycling system and succeed almost 100% conversion to ammonia. One of the process byproducts is carbon dioxide, which we will going through in the following slides. So we will go through first into the right hand side diagram, which is the steps to produce ammonia. Firstly is sulfur removal. The first step is to remove sulfur. So why is that happen? Why is that is the process? So it is because sulfur compound will deactivate catalyst used in the following step. Then at the catalytic reformer, the sulfur-free feeds are used to form hydrogen with carbon monoxide. In shift conversion, the carbon monoxide will change into carbon dioxide plus more hydrogen, and then the carbon dioxide will be removed in the stage. And in methanation, the process is to clean up. So we are going to look into the ammonia synthesis reactors or converter. There are many types. Actually, there are many types of converter, such as Kellogg, ICI, Topso, Youth, Prong, and Haldor. But we will narrow it down to Kellogg and ICI type only. So without any delay, firstly is Kellogg. It is built with 3 beds, but often described with only 2 beds. Why? It is because the second and third beds have no significant functions. Firstly, we need to know that the reactor is also built with heat exchanger to make sure the feed into first bed and the output gas from the first bed have thermal exchange. So in addition to the mentioned heat exchanger, the quench gas flow, aka coolant, is also used for controlling the temperature. Next, once the feed enters the reactor, it will pass through the beds and gets shipped and gets slightly heated. So kiranya daripada feed tu dia akan masuk jalan daripada sini ke sini, masuk ke sini, dan dia akan tembus terus ke sini dan akan masuk ke bed 1. So from the bed 1, yang the output gas yang keluar ni ialah output gas. So when reaching the end of the reactor, it will pass through the shell of internal heat exchanger and its temperature reach 400 degrees Celsius. So in the tubes of the heat exchanger contain the output gas from the first bed. So output gas tu akan masuk ke dalam tube exchanger ni daripada bed 1. So the quench gas is used to control the inlet temperature of the first bed. The required temperature for inlet of the first bed is 371 degrees Celsius. So dia nak masuk dalam bed 1 ni, 400 degree Celsius ni dikurangkan menggunakan quench gas aka coolant kepada 371 sebelum dia masuk kepada bed 1. So next, the output gas after warming up is then entered to first catalytic bed again. When the gas passes to first bed and the reaction is taken place, its temperature increases and reaches 496 degrees Celsius. It then enters the tubes of the heat exchanger to cool it down. So kita tahu gas tadi keluar dari sini, lepas tu dia akan masuk semula dalam bed 1 ni, sebab dalam reaktor ni ada synthesis loop, maksudnya dia akan gunakan semula, dia akan sampailah reaction tu terjadi kat bed 1. So after that, gas is then entered from top of the second bed. So dia akan masuk sini, gas tu akan keluar daripada heat exchanger ni, akan masuk ke dalam bed 2, and no specific operation is carried out between beds 2 and 3. In fact, these two beds act as a single bed whose length is twice the length of each bed. So, and the catalyst of this reactor is magnetic ferroxide. So, the benefits from the Kellogg reactor is we can keep our costs down, and secondly, it is safe to say that it is low pressure drop. It have low pressure drop and also easy installation, and finally we only need to use only small amount of catalyst. The second type of reactor we need to discuss is ICI type, lozenge quench converter. It is basically almost same principle used in fixed bed reactor. It is simple concept but suffered high pressure, and it's also adiabatic reactor. And so that's all from me. Assalamualaikum warahmatullahi wabarakatuh.
Bismillahirrahmanirrahim. My name is Akram Mujahideen 1182317, and I will continue this presentation. So the topic is the methanol synthesis or production of methanol. So as we all know that to obtain methanol is by one of the method is natural gas, which is the methane gas CH4. Methane gas is used as a raw material to produce our product, which is the methanol. So, what is the function or uses of methanol in the industry? The first one is act as a feedstock to produce organic compound. So, what is the organic compound such as methanol, ethylene acid, dimethyl ether, and also MTBE, or we call it methyl tertiary butyl ether. So the next one is act as a source of fuels. So as we all know that methanol is flammable and also with low percentage by mass of carbon. And lastly, methanol also act as a solvent, which is the methanol will be added to the ethanol to give methylated spirit used as an industrial solvent.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fidaus bin Muhammad Zawawi. So today I will introduce to you about the methanol synthesis or the production of methanol in industrial process. So actually the methanol synthesis, we have two methods or we have two ways to produce methanol. So the first way is a direct conversion of methane. So here we have methane CH4 plus with the oxygen and also produce the methanol. And the second method that are more commonly used in industry is using the syngas or synthesis gas. So what is syngas? Okay, syngas is actually the mixture of hydrogen and carbon monoxide. Okay, and the main objective of the syngas is actually to ensure that the hydrogen molecule here hydrogenate the carbon monoxide in order to produce the methanol. Okay, now we're gonna do this experiment or this process in high temperature and moderate in high pressure and moderate temperature condition, but more importantly is in high pressure. Okay, now we also have the problem. As you can see here, this is the desired chemical equation which we are producing the methanol, but also we have the side reaction which is methane, and of course we don't want to produce the methane. And more importantly is the nature of this reaction. As you can see here, this is the undecided reaction. The nature of the reaction, we will be going to produce alcohols and hydrocarbons. Okay, so what type of alcohol that we are producing is actually alcohols in high weight. For example is ethanol. Okay, ethanol. Okay, ethanol with 2 carbon and 1 hydroxyl group, and also propanol, 3 carbon and 2 hydroxyl group, and also hydrocarbon, for instance is ethyl ether. Okay, ethyl ether, oxygen, and also 2 methyl group. Okay, hydrocarbons. And of course we don't want all these side reaction. We don't want the alcohols, hydrocarbon, and then we will need to separate all these using a series of phase separator and distillation column. And this reaction is carried out using catalyst, and the catalysts used are typical catalysts of transition metal. For example, zinc, chromium, mangan, aluminium. So all these are transition metal catalysts. Okay, so this is the schematic diagram of methanol synthesis as you can see here in the picture. Okay, so we start here. Okay, the raw material or the syngas, the hydrogen and the carbon monoxide are used in a molar ratio of 1 2. So 1 is the ratio of carbon monoxide and 2 is the ratio of hydrogen. So why hydrogen have 2 molar ratio? Because we want this hydrogen to hydrogenate the carbon monoxide in order to produce the methanol. Okay, then the mixture is compressed to 200 to 350 atm. So we increase the pressure drastically because as I stated before, we are going to be in the high pressure. Okay, now let's see in this part. Okay, in this part, this is the more technical on the puzzle part. Okay, we will have the recycling material. So as you can see here, recycle. So we will be recycling material because we don't want to waste the material. So what are the material that are being recycled? For example is hydrogen. Hydrogen will left over, or sometimes we have carbon monoxide, or even water vapor also left over from this reaction. Okay, and all these recycled material are in the gas form. That's why we recycle this material. Okay, so start here. Okay, so this is the mixture. Okay, mixture of syngas. Okay, then here after we mix all the mixture and then we pressurize and get the correct temperature, we will bring all this material to a reactor. So this is a reactor. Then As I stated before, this reactor contains a catalyst, a transition metal catalyst, and the reaction occurs in this reactor. And this reactor will operate at between 300 to 375 degree Celsius. So after the reaction completed, most of the material are going to be converted to methanol. So here, most of the material are going to be converted to methanol, but we have also some material that are left over in the gas phase, which is hydrogen, carbon monoxide, and water. So this gas will be recycled back. This gas will be recycled back to the reactor, and only the product of the methanol, which is in a liquid form, will continue to enter this container, this pink container, and the liquid of methanol will be here as a liquid, and all the gases after the compression or after the reaction in the reactor will be recycled back, will be used back in this reactor. Okay. Okay, now we have most of the material is right here, right? So now we got a cool down. So we got to cool down all of this material to a liquid state. Okay, so this material got a cool down. So what happened here is that we will bring this material to a container here. Okay, to this pink container. So what happened in this pink container is actually the phase separation. See, the phase separation occur, which is in the phase separation, methanol and the other high molecular weight compound, which is in the liquid phase. Okay, in the liquid phase are here, are in the container, enter the liquid phase. Okay, and the unreacted feed, which is the gas. Okay, the gas is produced as the gas phase. Okay, so then the gas will evaporate and recycle back to the reactor. So in here, in this pink container, we will have the liquid of methanol, alcohol, and also hydrocarbons. Okay, now we need to pay attention here. So we have our methanol here, right, in the pink container. So this is a liquid form of methanol and alcohols and also the hydrocarbons. Then we will depressurize the liquid to 14 atm. Okay, let down to 14 atm. Further depressurize to about 14 atm to enter second phase separator that produce the fuel gas. So what happened here is actually, as we know, when we depressurize material, we favor to form more gas, or we favor more gas formation. So as this material or this mixture depressurize, okay, most of the volatile gases, okay, we send back as the fuel gas. So this gas will evaporate, and the liquid that left over in the second container is the large percent of methanol and some of the alcohols and hydrocarbons. Instead of we have the fuel gas, because fuel gas is more volatile, then it will be evaporate here. Okay, okay, okay. Now here we call this liquid is the crude methanol. So this liquid after depressurized, we call this liquid as a crude methanol. So this crude methanol we gonna be treated and sent to a mixer. So this is a mixer that contain potassium permanganate, KMnO4. Okay, that contain potassium permanganate. So this KMnO4 that act as a oxidizer will remove traces of impurities and also ketones and aldehydes. Okay, so now after the crude methanol entering the mixer, then we have to keep going and we send this to the ether tower. Okay, we send this to the ether tower. So why we entering the ether tower? Because this easy to separate. Okay, Why easy to separate? Because the ether is a non-polar. So this ether, oxygen, and this methyl group here and methyl group here. So this ether is a non-polar molecule, and all the other alcohols will be the polar molecule. So the volatility of this ether is very high. So that's why this ether will be left over in this ether tower at the top of the tower. So that methyl ether as a top product, and we separate most of the ethyl ether, and the bottom will be the methanol. So the bottom here will be the methanol and other alcohol products. Okay, so next we will bring the methanol and other alcohol product to the second tower. Okay, as the first tower we successfully separate the ether from the mixture. Okay, now we will bring all this methanol and other alcohol products here, now entering the methanol tower. Okay, now entering the methanol tower. Then we will separate the methanol as the most volatile material. So methanol is the most volatile material. So we will separate this left over the methanol tower. So then we will take over the heavy alcohols and some of water here at the bottom. So why water is at the bottom? Because we know that this water is the most polar material compared to methanol and heavy alcohol. So then at the last separation, we will have methanol, other high molecular weight of alcohols, and also water. And that's all the overall process of the methanol synthesis. The first part is the reaction. So the reaction in a reactor. Okay, then we will have the separation here, separation of volatile gas, and then we will remove the impurities in the mixer, and then the last part is distillation, which means we separate the ether and the heavy alcohols in these two distillation tower. So then we will have the pure methanol here. Then this methanol is our desired product from the starting material, which is the syngas. And this is how the methanol synthesis work from the syngas, and lastly produce the methanol. And I think that's all from me. Thank you.
So we meet again on the last part of methanol synthesis, which is direct conversion of methane. So what is direct conversion of methane is it's actually methane is converted into methanol with the use of metal oxide catalyst and also at high temperature and high atmospheric pressure. Okay, so three main components that we need in the direct conversion of methane. So when we use direct conversion of methane instead of the syngas method, it's actually significant efficiency increase, which is this method is quite straightforward and very simple. And then no, we can see at the chemical equation there is no side product produced, and then no carbon dioxide produced, as I mentioned before, there's no side product produced, so no carbon dioxide will produce in this method. And lastly is a low yield method, low yield that will produce at the final of the process, which is because of the equilibrium process of this method, as we can see at the chemical equation. Alright, I think that's all for this part. The presentation will be continued by the next presenter.
Hi, Assalamualaikum everyone. I'm Irfan and we're now at the last part of the downstream reactor, which is the Fischer-Tropsch synthesis, aka FT synthesis. As the name suggests, it was discovered by Franz Fischer and Hans Tropsch in the 1920s, and it is used to convert gas into long aliphatic hydrocarbon. So why did they do that? Simple, because 1920 was on the World War II period in which the Germans needed fuel for war. In other words, FT synthesis is used to make synthetic fuels, which describe the post-war events in which the African used this knowledge to generate synthetic fuels in the 1950s, and the technologies evolved since that, which includes the usage of catalysts, and also reactor design. Now, we look up to the process principle, which I tell you it is quite simple. Point number 1 states the general equation for the FT synthesis. And as we all know, FT synthesis produces synthetic fuels that contains of long hydrocarbon chains, which is why the coefficient N is usually between 10 until 20. And if we look at point number 2, the process usually takes in temperature between 150 until 300 degrees Celsius, and it is highly exothermic. This is where reactor designing part is crucial because the reactor must be able to operate and constantly stay in between the optimum temperature range to work efficiently. Moving on to number 3, catalysts used are usually from transition metals like cobalt, iron, ruthenium, and also nickel. But nickel produces methane, which point number 4 explains that methane and sulfur are one of the undesirable conditions when the process takes in. Now this is a block flow diagram, which is a simplified process that incorporates FT synthesis. We can observe that FT synthesis is just a part of a process. The full process consists of many other utilities. As we can see, number 1 is where the gasification occurs, which prepares the reactant before entering the FT synthesis reactor. And then we can see that number 3, 4, 5, which is wax hydrocracking, hydrogen recovery, and product storage, which actually helps to refine the product, to touch up the product, become more enhanced material. So we have reached the end of our presentation. Thank you for listening. I hope you guys understand, and if you guys don't, just don't forget to ask the question in WhatsApp group. Okay, until next time, bye bye.